right, let's do this review of Unit 5, Learning Targets 5 through 9. So the first learning target is I can explain the signs of a chemical reaction. I can interpret the components of chemical equations, like the reactants, the products, the subscripts, the coefficients, and the phase labels. So first question, name 2 examples of a chemical reaction that you're in the presence of every day, and some evidence to indicate that these are chemical reactions. I'm going to do a candle burning. I like to burn a lot of candles. There's light, there's heat released. I should say thermal energy released. Okay. And then I'm trying to think of one where there's bubbling. That is an everyday kind of one. I'm not going to do baking soda and vinegar because that's not like you just mix those together every day. I can't think of one with bubbling. Yeah, I can't think of one with bubbling. I know one that I'm going to say is formation of rust, because you see that just around things getting rusty, nails and things like that on my back deck. So that is a color change in that formation of rust. It's turning from like a steel color to like an orange color. Other signs of a chemical reaction that are not in mine, I already mentioned the bubbles as one, but I think these are listed in, let's see, did we list these in here? Language of chemistry, light, heat, color, formation of a gas, formation of a solid is another one there. Okay, for the reaction below, do the following. Highlight the products in pink, okay? The products are to the right of the arrow. So these are my products. Highlight the reactants in blue. Those are to the left of the arrow. Box the coefficients. Coefficients are the numbers out front. There's a 1 here. I could put it in if I want, or I can just leave it blank. Underline the subscripts. So there's a subscript here, here. Those are the small numbers that tell you how many of each type of atom there are. And star the phase labels, the states of matter. Okay, next learning target. I can describe, characterize, and give an example of each of the following types of reactions: combination, decomposition, and combustion. I can use reaction classification to predict the products of those reactions. Number 3, name the type of reaction for each of the following unbalanced reactions below. Don't worry about balancing them yet. So the first one here, we've got combustion. I recognize it because it's got carbons and hydrogens plus oxygen, making carbon dioxide and water. The next one is sort of like the AB breaking apart into A plus B. That I recognize as a decomposition. And the last one is the opposite of decomposition, 2 things combining and forming one product. That is a combination, sometimes called a synthesis reaction. Okay, we're going to do a little balancing in this one, which is kind of ahead of schedule since that's learning target number 8. But we're going to predict the products, balance the equation, and name the reaction type. Let's name the reaction types first. Letter A is 2 things adding together, so that would be a combination. And in combination reactions, in order to write the products, we're supposed to think about crisscrossing the charges of the new relationship. So actually, let's do that right now. So Na and F are together now, but we have to check charges. Na is right here, it's got a +1 charge, and F is right here, it's got a -1 charge. So while some people would want to slap these together and just write NaF2, That's not right. It's just NaF because the charges cancel out. And now we're going to balance. So NA's on the left, 1, on the right, 1. F's on the left, 2, and on the right, 1. So in order to balance this, we're going to need to put a 2 in front of the NaF. And that now changes the NA's to 2 also. So we need to put a 2 in front of the Na on the left. So the final coefficients would be 2, 1, 2. Next, we've got one thing breaking down. That's sort of like AB breaking into A plus B. So that would be a decomposition reaction. When you think about these, you want to think about make everything alone. So have a breakup, and then think about Hofbrinkel, the 7 diatomic atoms that always get a 2. So for this one, we're going to break them up into Ag plus N. And then we're going to look, and okay, N is in Hofbrinkel, so it's going to get a 2. Okay. For balancing, we've got 3 Ags on the left and only 1 on the right, 1 N on the left and 2 on the right. One of the tips is to make odd numbers even. So I'm going to put a 2 in front of that Ag3 to make it be 6. And now that is 6 Ns. So to compensate, we're going to need a 6 in front of the Ag and a 3 in front of the N2 to also make that be 6. So the coefficients are 2, 6, 3. And the last one I recognize as fuel plus oxygen. That's a combustion reaction. So our products we know are going to be CO2 and H2O. So to balance, we're going to do the Cho method. C's, then H's, then O's in that order. 6 C's on the left, only 1 on the right. 14 H's on the left, only 2 on the right. 2 O's on the left, and 2 plus 1 more, 3 on the right. Okay, let's start balancing. So I'm going to put a 6 in front of the CO2. I'm not going to do the O's yet, because I'm also going to fix my hydrogens. So 7 makes 14 hydrogens. So everything's balanced now except for the O's. So here we've got 6O2, that's 12 O's, plus another 7 O's. So that's a total of 19 O's. What's half of 19? 9.5. So this is 19, this is 19. So everything is balanced. 1, 9.5, 6, 7. But we cannot leave a decimal out front. So we're going to need to double everything. So our final answer is 2, 19, 12, 14. That's it. Next, we're moving on to energy diagrams. It says, I can draw and label an energy diagram for a chemical reaction. It says, sketch an energy diagram for the combustion of coal to form carbon dioxide. Okay, so carbon plus oxygen gas, since it's combustion, is going to make CO2. The heat of reaction is negative. That means this is going to be exothermic. So we have to know that the shape of an exothermic reaction is one that goes up and way down. We write out our reactants at the start, coal plus oxygen, and then we write out our products toward the right. Okay, the heat of reaction is the difference between the reactants and the products. So that's a negative 394 kilojoules per mole. Breaking bonds is happening on the way up. It didn't tell us the activation energy exactly, but we know that it's that blue line. The transition state is the tippy top, where all the atoms are single because the bonds have broken. And then the way down, new bonds forming, is the yellow. Is the energy required to break the bonds, which is the blue, greater or less than the energy released upon forming bonds? So which is bigger, the blue line or the yellow line? Well, the answer is that the energy released upon upon forming bonds is greater than the energy required to break bonds. This is true in all exothermic reactions, such as this one. So in combustion reactions, there's always more energy released when the new bonds form. So you're always ending up with a negative heat of reaction, which means that it's releasing energy overall. Okay, we've already done some balancing. Let's do a little bit more here. So here we've got Ag and S, 1 Ag on the left, 2 on the right, 1 sulfur on the left, 1 on the right. And so we need a 2 in front of the Ag, and we're balanced. For the next one, we've got aluminums and oxygens, 2 on the left, 1 on the right, 3 on the left, 2 on the right. A couple different approaches, but I would make odd numbers even. So I would slap a 2 out front to make that 3 oxygens become a 6, which means then you need a 4 in front of the Al and a 3 in front of the O2 to make that be 6. Then you're all balanced. Letter C, we want to use the Cho method. C's, then H's, then O's. 14 carbons on the left, only 1 on the right. 30 hydrogens on the left, only 2 on the right. 2 oxygens on the left, and 2 plus 1, 3 on the right. Okay, let's put a 14 in front of the carbon and a 15 in front of the H2O, so that our carbons and our hydrogens are all balanced. And now how many O's is this? 14 times 2 is 28 O's plus 15 O's makes how many? 28 plus 15, 43 O's. So what's half of 43 O's? That's 21.5. So that makes 43 O's on each side. But can you leave a decimal like that? No. So you have to multiply everything by 2 to get your final answer. 2, 43, 28, 30 for your coefficients out front. Then there's a simple mole ratio question. What is the mole ratio of C14H30, is what that's meant to say, to CO2? So that would be 2 moles C14H30 to 28 moles CO2, which is the same as a 1 to 14 ratio if you simplify that. All right, we're in the home stretch here. I can use a balanced chemical reaction to calculate the amount of reactants and products for a reaction, aka stoichiometry. And I can determine the percent yield from the actual and theoretical yields of a chemical reaction. Okay, so let's use this magnesium reaction here. If you have 250 grams of oxygen gas, that's our chemical A, and an excess of magnesium, how many grams of magnesium oxide can you make? Okay, first step, we're actually right here on our mole map. We have 1 mole A on the top divided by blank grams of A. And then we go to the periodic table and we say, hey, how much does 1 mole of O2 weigh? Well, 1 mole of O is 16 grams, and there's 2 of them. So that means the molar mass is 32. Next step, we're going to be using the balanced chemical equation. Blank moles O2 on the bottom, blank moles MgO on the top. So for every 1 mole of O2, you make 2 moles of MgO, a 1-to-2 ratio. And our last step is to convert our moles of magnesium oxide into grams of magnesium oxide. So we go to the periodic table and we say, okay, how much is it for Mg? 24.305. Oops, I don't know why I wrote a 4. Plus oxygen is 16. So 40.305. And I multiply everything across the top. So in my phone right now, I'm doing 250 times 2 times 40.305, and I'm dividing by 32, and I'm getting 629.8 grams of MgO. You can round to 1 or 2 decimals is fine. So what if you actually make 601 grams? The percent yield is your actual yield, divided by your theoretical, times by 100. So we actually made 601 grams. We were supposed to make 629.8 grams. So how well did we do here? 601 divided by 629.8 is times 100 is 95.4% yield. Not bad, that's an A. Last one, it's putting balancing with stoichiometry question, and it's a little bit different. So first, let's balance and notice that we can actually keep our polyatomic ions together because NO3 stayed together on both sides, and so did PO4. We've got 1 magnesium on the left and 3 on the right. 2 NO3s on the left, 3 on the right. 1 Al on the left, 1 on the right. 1 PO4 on the left and 2 PO4s on the right. So first step, don't start with trying to do anything with an O or an H. So let's do magnesium. There's 3 on the right, so let's put 3 on the left. That messed up our nitrates. Sorry, I can't speak. 3 times 2, that's 6. So now we need a 2 in front of this because 2 times 3 would make 6 nitrates on that side. And that messed up our aluminums. It made it so it's 2. So now going back to the left side, we need a 2 in front of this Al, which actually helps us out because now there's 2 phosphates. So everything is balanced. Okay. How many moles of Mg3PO42, this is our chemical B, would be produced from 112 grams of Mg3NO32 and an excess of our AlPO4? Okay, so we're starting with 112 grams of Mg3NO32. So this is going to be a long molar mass to calculate. Okay, blank grams of Mg3NO32 is equal to 1 mole of Mg3NO32. Okay, we can do this. Mg. So Mg is 24.305 times there's 3 of them. So let's just do that part first. 24.305 times 3. So Mg times 3 equals 72.915. Let me go back and look at this. NO32. Okay, so NO32, that's 2 times nitrogen, and that's 6 times oxygen. So 2 times nitrogen Nitrogen is 14.007. So times 2, I can do that in my head, is 28.014. And 6 times oxygen, oxygen is 16. I'm not doing that in my head. That is 96. So we have to add all these things I'm circling together to get the molar mass. 96 plus 28.014 plus 72.915. That's a molar mass of 196.929. Now there's some good news. We only have one more step because this asks us to stop at moles. So, okay, now we've got to convert moles of Mg3NO32 into moles of Mg3PO42. I just realized that this equation is written wrong here. Interesting. So we need to go back. Go back. I was like, there's something wrong with this. Sorry, guys. This is good practice. This is real world right here. This was written wrong. It should be MgNO32. Okay, this would be a little easier. MgNO32. I just started thinking, I'm like, how is this even possible? Okay, blank grams of MgNO32, 1 mole MgNO32. Sigh. Okay, going back to this. So we don't need Mg times 3, we just need Mg. So this should be 24.305. Erase the times 3. Plus, it's still NO32. Okay, so 24.305 plus 28.014 plus 96. Slight change, 148.319. Okay, and last but not least, blank moles of MgNO32, blank moles Mg3PO42. This is what we get from the balanced equation. So in front of the MgNO32 is a 3, and in front of the Mg3PO42 is a 1. So this is a 1:3 ratio. So now I multiply everything on the top divided by everything on the bottom. So 112 times 1 times 1 divided by 148.319 divided by 3. Answer, 0.25 moles of Mg3PO42. How many grams is that? So it's not really an easier problem because it eventually is making you calculate molar mass anyways. Mg3PO42. Maybe it wasn't useless that we calculated the Mg3, although now I forgot what it was. Okay, so I'm doing this in black. Mg times 3, so 24.305 times 3, that's 72.915, and then it's PO42. PO42, that's 2 P's, so that's right here, times 2. So that's 30.974 times 2. So the P's are 61.948. I'm going to circle that. And then the O's is 8 because it's 04 times 2. So 8 times 16. 8 times 16, 128. So we have to add the oxygen plus the phosphorus plus the magnesiums all together to get the molar mass. Final answer here, 262.863 grams of Mg3PO42. Multiply across the top. Answer 65.7 grams of Mg3PO4-2. What would the percent yield for the above reaction be if you had an actual yield of this? Oh, what the heck? Your actual yield should not be higher. 0.25. Okay, that seems right. Hang on, I'm questioning if something went wrong somewhere. MgNO3 2. So 6 oxygens plus 2 nitrogens. That's 28.014 plus. So that's right. 112 grams of this. And then 3 moles of that. 1 mole of Mg3PO4-2. Okay. 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 We got an actual yield of 80 grams and our theoretical yield was 65.7. So 80 divided by 65.7 times 100, we got a 121.8% yield. Usually you don't get over 100%, but your error can be off too. So there you go. Nice work, everybody.